Okay, here we are. We are going to kind of combine two sections today. It's going to be section 5.8, which talks about the fundamental theorem of calculus, and we're going to start in 5.9, which actually applies it. So what we're going to work on are integrals again, finding that area under the curve. And I just want to review what we've done in the past, well, one way. We want to look at the integral from 2 to 5 of the function x squared plus 1 dx. So what we're actually finding when we set this up is the area under this curve from 2 to 5. So if I do a quick sketch of that, that's a parabola with the vertex up 1. And I'm looking at the area from 2 to 5. And we have done this problem many different ways through the year. We counted squares. We did trapezoids with the trapezoid rule. Then we did it with rectangles with the Riemann sum. And we did lower sum, upper sum, and midpoint sum. We're going to use our program to approximate the area under the curve from 2 to 5 with midpoint sums with 6 rectangles. So that would be M6. And we're not going to do it by hand again. So I'm going to run the program, the Riemann program. Oh, that's not what I wanted. That's a long program. Okay, program, Riemann. So if I put my function in there was x squared plus 1. The lower boundary was 2. The upper boundary was 5. And I wanted 6 partitions. That's a midpoint sum, so that's number 4. And that gives me the area under the curve is about 41.9375. 41.9375 square units under that curve. Okay, what we're going to do now, from now to the end and forever in calculus, is the fundamental theorem of calculus. How important does that sound? Fundamental theorem of calculus. And what it does is it finds the exact area under the curve. All the ways that we found the area under the curve before have all been approximates. This is our first time we're going to be exact. And here's what the theorem says. If function f is an integrable, that means you can actually find the integral of it, the antiderivative. The antiderivative exists. So if it's integrable, and if g of x is the antiderivative of f of x, then here it is, the integral from a to b of f of x dx can be found by evaluating function g of b minus g of a. Okay, oops, sorry. So if f is an integrable function, and if g of x is that antiderivative function, then the integral from a to b of f of x, in other words, the area under the curve, is g of b minus g of a. So what that's telling you to do is do the antiderivative of this, find that function, and we spent a lot of time doing that. And then all you have to do is substitute in the upper boundary, substitute in the lower boundary, and subtract those two results. That will give you the area under the curve. So let's redo that problem I started with and do it with the fundamental theorem of calculus. So it's a redo here, so I'll just rewrite it. From 2 to 5, x squared plus 1 dx. So the first thing we have to do is do the antiderivative. Remember, there's no inside here. We just do each term separately. So we do a little power rule. We're going to add 1 to the exponent times the reciprocal. Then I do the antiderivative of 1, which is x. And then I'm going to evaluate that from 2 to 5. And the way we do that is we just put a bar here from 2 to 5. That just shows you're going to substitute in these two values. And it's always the upper boundary substituted in first, work it out, minus the lower boundary substituted in and work it out. So this basically is our function g. Oh, I forgot my plus c. Jeez, plus c. So there's function g. It's the antiderivative of this. And now I'm going to substitute in the 5 and the 2. So the substituting is what we have left. So substituting in the 5, it's 1/3 times 5 cubed plus 5 plus c. Then I have to subtract whatever I get when I substitute the 2 back into that same equation. 1/3 times 2 cubed plus 2 plus c. Okay, working this out. Now it's just calculator work at this point. Quit. Okay, 1/3 times 5 cubed plus 5 is 46 2/3 plus c minus, and over here I've got 1/3 times 2 cubed plus 2, that's 4 2/3 plus c. So if I distribute the negative here, I've got 46 2/3 plus c minus 4 2/3 minus c. That minus gets distributed to both of them, minus and a minus. So you can see the c's cancel each other out. And if you think about it, that's going to happen every single time, because you're going to have a plus c and a plus c, and because I'm subtracting, this c cancels that one out. So from this problem on, we will never put a plus c on here if we have these boundaries. If there's no boundaries here, like before, we have to put the plus c. So now I just have to do 46 2/3 minus 4 2/3. The 2/3 cancel. That's going to give me an area of exactly 42 square units. So what we're doing today is just doing the antiderivative stuff and substituting in. So let's practice it. And that's your fundamental theorem of calculus. What you're finding right now, this is called a definite integral, where the ones with the plus c on them are indefinite integrals. So you've now just calculated your first exact definite integral. Definite integral, because you found an actual value for it. So we're just practicing fundamental theorem. Easy stuff, as long as you can integrate. So we want the integral from 2 to 5 of x to the third dx. So these should seem very easy because I'm not going to put them at the level we were doing them before. So doing the antiderivative here, you're going to add 1, multiply by the reciprocal. Not necessary to put the plus c because we're going to evaluate. I don't know why I picked 2 to 5 again. It's not always going to be 2 to 5. And now, top boundary goes in first. So that's 1/4 times 5 to the 4th minus, put the 2 in, 1/4 times 2 to the 4th. And then it's just calculator work. And we want to stay exact if we can. 1/4 times 5 to the fourth minus 1/4 times 2 to the fourth, 152. The integral of the, let's see, from 0 to 3 of the square root of 3x plus 1 dx. Okay, remember your skills from before. I like to rewrite this with its fractional exponent. So we are still doing the integral from 0 to 3 of 3x plus 1 to the 1/2 power dx. So here I do have an inside because there's an exponent that's not equal to 1 there. So the u is equal to 3x plus 1. And you could do this one in your head. You don't have to write this part out because you can see the derivative of the inside very easily here. So that u prime is 3 dx. I always throw a dx on there. So what I need to do before I can integrate this with my power rule is stick a 3 next to the dx. And I have to hit it with a 1 to do that, so I put a 1/3 out in front. So now it's ready to go with the power rule. 1/3. The inside stays the same. Add 1 to the exponent. That's going to give me 3/2. Multiply by the reciprocal. And then we're going to evaluate from 0 to 3. So I don't need the plus c when I'm going to actually plug numbers in. So substituting in the 3, I'll have 2/9 times the quantity 3 times 3 plus 1 to the 3/2 minus, substituting in a 0, 2/9 3 times 0 plus 1 to the 3/2. So don't automatically think that the quantity is going to be 0 just because the boundary is 0. You can see 0 plus 1 is still 1. That's going to give me a value here that I have to subtract. So now it's just calculator work, and this is sometimes where people mess it up. And you're best off to do two of these. You can do them separately, or you can use a table. I'll show you maybe a table is probably the quick way to do it because you got to do the whole problem twice. So the way to do that is go to the y equals, type your equation in. That'd be 2/9 times 3x plus 1 raised to the 1.5. Now if I go to the table, I want 0 and 3. So if I start at 3 and I go by 1s, I'll be able to get those two. So I got 7.0273 minus, and then when I put in a 0, 0.2222, and then just subtract and we'll have my answer. 7.0273 minus 0.2222. 6.8051. You could have typed this whole line in your calculator and gotten that answer. I don't really care how you get from here to here as long as you can do it using a calculator. Okay, let's try some trig functions. Let's go from pi over 4 to pi over 3 of cosecant squared x minus sine x dx. All right. No inside to worry about. Think of them as two separate problems. I'll even write them as two separate problems.